My name is Moritz Günther, and I'm the chair this afternoon. Our first talk is going to be Costanza from Palermo in Italy about high resolution X-ray spectroscopy from cool stars.
Okay. Good afternoon, everybody. And in this talk, I will review the most important results obtained with high resolution X-ray spectroscopy concerning the X-ray emission from late-type stars. When we want to understand the X-ray emission from late-type stars, we have to bear in mind that there could be different emission mechanisms. First of all, in late-type stars, we usually have coronal plasma, that is hot material located in the outer stellar atmosphere. In addition, if the star considered is a young star, still surrounded by a circumstellar disk from which the star is still accreting material, this material that falls onto the star following the magnetic field lines arrives near the stellar surface with velocities of a few hundred kilometers per second. So there, this material produces accretion shocks, and these shocks hit this material up to temperature of a few million Kelvin. So we can have in young stars also X-rays because of the accretion process. When we have accretion, we can also have outflows, and also in the outflows, strong shocks can form within the ejected material. And also in this case, we can have some shocks producing material hot enough to produce soft X-rays. And finally, we can also have X-ray fluorescence from cold material. Essentially, cold material is the stellar photosphere, or if present, a circumstellar disk. In this case, those cold elements can can reflect the X-rays produced by the hot stellar corona. In this talk, I will essentially focus on the first two emission mechanisms, that say coronal plasma and plasma heated in the accretion shock. You have to bear in mind that both these kind of emission are strictly related to the stellar magnetic field. So studying this kind of phenomena means studying, understanding something on the stellar magnetic field. Why late-type stars are able to produce magnetic field? Essentially, you need to have two ingredients for the magnetic field production. You need to have differential rotation, and also you need to have an outer convective envelope. That is the most important characteristic of late-type stars in allowing them to produce magnetic field. When you have these two kinds of internal motions, differential rotation and an outer convective envelope, so you will have a dynamo mechanism that is working within the star, and this dynamo mechanism is able to produce magnetic field which are quite high. The magnetic fields of late-type stars can be of a few kilogauss at the stellar surface. If we want to study and understand something of the corona of late-type stars, of course, this is an image of the solar corona, which is always our starting point if we want to understand something. What we know about the coronal plasma in late-type stars? We know that it is hot, it is at low density, and therefore its X-ray emission is usually optically thin. The typical X-ray luminosity of active stars can be up to 10 to the 32 erg per second, and it is possible to measure the level of activity of a given star by computing the ratio between the X-ray luminosity and the bolometric luminosity, and this ratio can be as high as 10 to the minus 3. As I said before, if we want to understand something of coronal plasma, we have to start from the solar corona, because for the sun, we have observation with a spatial resolution not available in stellar observation, and we have data with a very high signal-to-noise ratio. However, there is an issue that the sun is not an active star. The sun is slowly rotating, and so its X-ray luminosity is quite low. And so there are a lot of open issues because it's not so clear how we can scale up what we know for the solar corona up to the corona of stars that are much more luminous in the X-ray band. So for instance, it is not clear which are the physical properties of coronal plasma in active stars. It is not clear whether and how these coronal properties depend on the stellar mass, stellar rotation, or age. And if we want to focus on transient phenomena that are usually observed, for instance, in the solar corona, and depending on the phenomena we are considering also in the corona of active stars, if we want to understand something of flares or coronal mass ejections, the issue is much more complicated, how we have to scale up what we observe for the solar corona in the case of corona of active stars. I will briefly review, as I said before, some results obtained concerning this topic obtained from high resolution X-ray spectroscopy. For instance, it is possible to infer something on the special distribution of coronal plasma, because if you obtain an high resolution X-ray spectrum of a star that is rapidly rotating, that means the equatorial velocity along the line of sight can reach velocity of 100 km per second. If you obtain a high resolution X-ray spectrum of this kind of star, you can search for line broadening, because any line broadening would imply that you have significant amount of coronal plasma located at low latitude. In addition, you can also search for line shift, because if you detect line shift, you can have material located at a given longitude. This kind of analysis has been done for a few targets that are suited for this kind of studies, because those stars have very large equatorial velocity. And in all these cases, essentially what has been obtained is that coronal plasma is not uniformly distributed in the stellar atmosphere, but is mostly concentrated near the stellar poles, or is unevenly distributed concerning the longitude of the star. This is in some terms similar to what we observe for the solar corona. Coronal plasma are not homogeneous. However, the special distribution in active stars appears to be quite different, because while in the solar case, we observe a lot of coronal structures at low latitude, in active stars, it seems that the vast majority of coronal plasma is located near the stellar poles. Other important studies on the physics of stellar corona relies on the derivation of the emission measure distribution, the amount of emission measure that you have at different temperatures. It is an important quantity because obtaining these quantities is an easy way to compare different sources. For instance, I report here about a recent study in which 19 main sequence stars with different spectral type and different X-ray luminosity have been observed in high resolution X-ray spectroscopy. And the emission measure distribution has been obtained for all of these stars. And those stars the activity level of these stars have been parameterized by considering the surface X-ray flux. And the results obtained is shown in this plot, where you can see that the emission measure distribution of stars at different activity levels increases and becomes hotter and hotter. And it is useful to compare these emission measures and also compare those emission measures with predictions based on modeling of coronal structures, but also in this plot, as you can see, there is also a comparison with the emission measure distribution obtained for the sun, quiescent solar corona or solar flares or active regions, because you can understand the physical difference between the coronal structures in active stars or in the solar case. Another couple of recent studies instead derived the emission measure distribution of the plasma located in the stellar atmosphere using together X-ray spectroscopy and UV spectroscopy, because if you complement your X-ray data with also UV spectroscopy, you will enlarge the temperature range that you can explore, because UV spectra includes also lines that form at lower temperatures. So the aim of this kind of studies is to derive the profile of the thermal profile of the stellar atmosphere, starting from 10 to the 4 up to 10 to the 8 Kelvin. Those are the results that have been obtained in these two cases. And in addition to obtain, which is the temperature profile, the emission measure distribution in this large temperature range, the other important advantage is that once you have this model of the stellar atmosphere, you can also compute what is the predicted spectrum produced by the star in the high energy range. And in particular, you can compute what is the spectrum in the EUV band, which is a band that is not accessible via observation. And it is important to constrain the radiation produced by the central star in this energy band. because it is important for the evolution of exoplanetary systems. When we study coronal plasma, it is also important to study and understand the physics of flares. Flares are observed usually in stars as a rapid increase in the X-ray luminosity, in the X-ray flux. Those are just some light curves in which strong flares have been observed for active stars. We know a lot about the physics of flares because, again, the solar case represents the starting point for understanding what happens during this rapid increase in the X-ray luminosity. And thanks to solar observation, the so-called standard flare scenario has been developed. And what the solar observation tells us is that when you have the magnetic field, it can happen that the magnetic field changes its configuration, and in changing its configuration, magnetic reconnections can occur. And during those reconnections, the magnetic field loses energy, and this energy is transferred via accelerated particles to the lower layers of the stellar atmosphere at the base of the magnetic flux tubes where the reconnection has occurred. This large amount of energy that is deposited essentially in the stellar photosphere heats the material there up to temperature of 10 to the 8 Kelvin. This heated material evaporates moving upward, filling the above coronal structure, giving birth to what we observe in the X-ray band, this rapid increase in the X-ray luminosity. This material then cools down and goes back in the lower layer of the stellar atmosphere. If we are lucky enough to observe this kind of phenomenon exactly from the right direction and with, for instance, the HETG of Chandra, we can measure the velocity of this flaring plasma that is moving within the flaring loop. For instance, this is the light curve observed for an active star, in which you can see the first part of the observation is characterized by a strong flare, followed by a quiescent phase. The signal-to-noise ratio of this observation is so high that it is possible to perform time-resolved spectroscopy, and in particular, it is possible to search for line shifts in different lines, in different temperature, and in different time intervals. I report here just a couple of examples of the silicon-14 line and the magnesium-12 line. You can see in the upper part the light curve observed in these two lines and the profile collected for these lines in different time intervals. So you can measure the velocity of the plasma at different temperatures at different time intervals. And it has been observed that during the rising phase of the flares, the velocity probed by the hottest line, the silicon-14 line, is blue shifted. The line is blue shifted. So we are observing a significant velocity that indicates the material is moving toward us. While instead, the slightly cooler line, the magnesium-12 line, display a significant redshift in the decay phases of the flare. So we are observing exactly what is expected if we are observing the flaring loop just from above. First, a rising of the hot material, and then this material that cools down and goes back to the photosphere. This is the first X-ray detection of motion of plasma within the flaring loop. And it is an important observation because we can verify that the model developed for solar flares works also in this case. In this case, it is a flare that has an energy which is several orders of magnitude higher than the typical flares observed on the sun. Another important thing that solar observations teach us is that when we have flares, we usually have another important phenomenon that is associated to the flare, that is the so-called coronal mass ejection, because the energy that is released by the magnetic field is also used to accelerate outward and eventually eject material that was previously confined in the corona. This kind of phenomena are usually observed in the solar corona. This is, for instance, a movie obtained for It is a time period of 1 month of observation of the outer solar corona. And you can see how coronal mass ejections are frequent in the solar corona. But we can observe so well coronal mass ejection on the sun because we have special resolution. It is not easy to observe this kind of phenomena in other stars. However, even if it is not easy, it is important to detect whether CMEs exist also in active stars, because those plots again consider the solar case, solar flares and associated CME. You can compute what is the energy of the flare by considering the total energy radiating in the X-ray band. And solar observations tell us that the flare energy scale up with the mass and kinetic energy of the associated CME. It is important to understand the flare of active stars that have energies significantly higher are also associated to CMEs. Do those CMEs behave like a scaled up version of the solar CMEs? Several studies have been focused in trying to understand which are the consequences if the solar case can be extrapolated up to this high energy range. And the issue is that it is important to constrain that, because if the solar case can be extrapolated, then stellar CMEs should be responsible for a huge amount of mass loss rate and unrealistic amount of energy loss rate. It is important, therefore, to observe stellar CMEs to try to understand a bit more what happens in this energy regime, to constrain the evolution of the star, to constrain the evolution of its rotation, and also to constrain the evolution of exoplanetary systems. So we need observational information on stellar CME. And going back to the same Chandra observation I showed you before, the one in which the motion of the flaring material has been detected, it is also possible, thanks to this data set, to search for motion of cool material. In particular, this is the profile of the oxygen 8 line that probes material at 3 million Kelvin. And you can see that in this line, it has been observed a significant blue shift, but not during the flare, but after the flare, when the flare has already ended. And the only explanation for this cool material that is moving toward us after the flare is that this material is the CME material that has been ejected in association to the flare. And we are detecting this motion once the flare has ended its X-ray emission. So this was the first X-ray detection of stellar CMEs. And it is important because also this detection offers a new technique for search for stellar CMEs in other stars. The second topic I would like to discuss is the possibility to study the accretion process in young stars thanks to high resolution X-ray spectroscopy. It is important to study accretion because the accretion process is the way in which the young star and its circumstellar disk exchange mass, energy, and angular momentum. There are, however, several open issues concerning the accretion process. And thanks to high resolution X-ray spectroscopy, some of these issues has been addressed. In particular, as I said before, X-rays are thought to be produced at the base of the accretion stream. So let's focus on the base of the accretion stream. We have the star, and we know that material from the inner part of the disk arrives near the stellar surface with velocities of a few hundred kilometers per second. There, because of this velocity, at the impact with the denser stellar atmosphere, this material produces strong shocks, and these shocks reduce the velocity of the infolic material by a factor of 4. The density increases by a factor of 4, and the post-shock temperature is expected to be related only on the pre-shock velocity. And because of the value of the pre-shock velocities, the post-shock temperature is expected to be of a few million Kelvin. Thanks to the high-resolution X-ray spectroscopy, it has been possible to identify this emission in young accreting stars because high-resolution spectroscopy allowed us to measure the density of the X-ray emitting plasma. And it has been observed, thanks to Chandra and XMM, that in all stars where there is no accretion, the density of the material at a few million Kelvin, as probed, for instance, I report here the neon 9 triplet in all non-accreting star. The plasma at a few million Kelvin has a low density. It is plasma that is located in the corona. Conversely, when we observe young accreting stars, in almost all cases, the plasma at a few million Kelvin has a high density, indicating that the source of this plasma is not coronal, but it is plasma heated in the accretion shock. Several studies focused on measuring the main properties, essentially density and the temperature of this post-shock material. And in addition, in one case, for the nearest accreting star, it has been possible also to measure the post-shock velocity. Because for TWR, which is the nearest young accreting star, it has been acquired a Chandra HETG spectrum with a very high signal-to-noise ratio. And so it was possible in this spectrum to search for line shifts that are expected in the case in which this material is moving toward the inner part of the atmosphere. This is just an example of the profile of one of the neon 9 lines, but all the soft lines in this spectrum are redshifted. And as you can see in this case, a significant redshift has been detected in these lines, but also in other lines. And the amount of the redshift is something like 50 kilometers per second. And in this case, so this velocity is the final confirmation that this material is located in the post-shock. And this measurement allows us also to infer the geometry of the accretion stream, because we know which is the velocity along the line of sight. We know which is the intrinsic velocity, and so we can infer the angle under which we are observing the base of the accretion stream. And in this case, it comes out that this accretion stream is terminating at low latitude on the stellar surface, while usually it is thought that accretion streams terminate near the stellar poles. So measuring the velocity of the post-shock material is important also to constrain the geometry of the accretion. There have been different studies always based on high resolution X-ray spectroscopy of the radiation coming from the post-shock. I just cite here some of them because, for instance, you can measure the abundances of this material, and the abundances of this material reflect the abundances of the inner disk. So you can probe whether the inner disk has suffered some chemical segregation. You can also search and find rotational effect that allows us also to constrain the geometry of the accretion stream. And you can also search for short-term variability that would imply some intrinsic variation in the accreting material. So this is the summary of the results I cited in this talk based on high-resolution X-ray spectroscopy for what concerned the physics of stellar corona and the physics of accretion process in young stars. This last slide I want to show you is instead focused on what we can expect from future X-ray missions. In all the cases for the missions that are already planned or proposed, we hope to have a resolution X-ray spectroscopy with larger effective area than the instrument that we have nowadays. A larger effective area will imply that we can enlarge the sample of the target that we can explore with high resolution X-ray spectroscopy, and we can also probe what happens on short time scales. So in my opinion, concerning the topics discussed in this talk, that means that we can routinely search for stellar CMEs with these new future X-ray missions. We can study in detail the physics of stellar flares that have energies significantly higher than the solar ones. We can measure the velocity of the accreting material and so constrain the geometry of the accretion stream. And we can also explore what happens in the accreting material on short time scale. Okay, that's it, and thanks for your attention.
Thank you for an excellent summary. Are there any questions in the live audience? Or has everything been answered? Anyone?
Hi, nice talk. I have a question about this measurement of the, you had the 51 kilometers per second measurement, which is very high precision. Can you actually trust this result? Given what we've just heard about atomic uncertainties, and also there is this line width. So some of the gas looks to be
okay, in the case of this kind of spectra, the line width is simply due to instrumental effect. We tested the absolute wavelength accuracy of the Chandra gratings by measuring the position of lines produced in case in which you have no radial velocity. So we checked that the Chandra accuracy is precise up to this kind of errors when you have well-exposed line profiles.
Okay, that's very impressive. Thank you.
You're welcome.
Thank you.
Hi, Costanza, great talk. I was really interested in the positive detection of a CME. Were you able to get an estimate of the mass of the CME, and was it consistent with what anyone thought it was, or was it kind of wimpy?
The mass of the CME has been estimated from this data. And the mass is coherent with the extrapolation of the solar case, while instead the velocity and the kinetic energy is orders of magnitude below the extrapolation of the solar case.
The mass is consistent, but the energy is low.
No, yes.
Okay.
We talked a lot about line profiles or line shifts. With high resolution spectroscopy, of course, we do boring things too, like just measuring line fluxes. Can you maybe comment a little bit on how high resolution, or what high resolution does to ask for abundances and temperatures compared to low resolution spectra?
Can you explain a bit more your question? I didn't, sorry, I didn't understand.
Yeah, I mean, this is all really cool stuff.
Yeah.
But even if you don't measure line shifts, if you just have the flux,
okay,
that's still important.
Of
right?
course, it's still important because, for instance, all the derivation of the mesh distribution, it's based on simply line fluxes. I did not cite all the studies focusing on the abundances of coronal plasma, which are also interesting because we observe anomalous abundances in coronal plasma. And of course, in those cases, you simply need to have line fluxes. That is already a lot of stuff to study the physics of this kind of sources, of course.
Thank you. Any more questions? And we'll thank the speaker again. You can either clip it on or put it around your neck, whatever you prefer. Or was it it's a magnet? Our next speaker is Richard Ignace, who is going to tell us about line profiles from more massive stars than we heard about in the last talk.
Well, thank you all very much. So I'm going to talk, basically this is a theory talk. I'm going to work kind of in an idealized space and discuss the process of building spectral line profiles for purposes of producing diagnostics of kinematics, quite honestly. I really enjoy taking kinematic prescriptions and trying to see how far I can push them to map between, say, a synthetic line profile shape to spatial mapping of different properties of the source. It's kind of about massive stars. Massive stars is usually where I find my applications. Frozen up, there we go. Is usually where I find my applications. But it can have applications to other places, such as Vikram's talk this morning about supernovae, and he had shell blur, I think it was called, looking at all kinds of different effects on line profiles. But anyway, I'm kind of up here in the upper left of the HIR diagram, radially driven winds, blow up of that section, so Wolf-Rayet stars, O stars, that sort of thing. This class of objects present all kinds of interesting possibilities for shocked regions and X-ray productions, colliding winds, Winds are very fast at 1,000 kilometers a second, have magnetospheres with channeled wind streams, essentially what I call self-collision. And then they also have instabilities, and you can make shocks inside the wind itself and have distributed wind shocks. I'm going to spend a little bit of time in a couple of these topics, but this one in particular, you basically have this multi-component flow where you have cool wind that may, if it's thick enough or dense enough, can do some photoabsorption in situ right around where the hot gas is actually produced itself. It's an area that has gotten a fair amount of study for a variety of reasons. We care about mass loss rates for massive stars and how that fits into the narrative of galactic evolution, production of GRBs and gravitational waves, black hole remnants, and things like that. And so, for example, here's one of Zeta Pup with almost 1 million seconds of Chandra time and just producing an amazing spectrum. I like this because you actually detect the continuum at high energy, low wavelength. I think that's the first time that was done in a massive star circumstellar environment like that. Keep hitting the wrong button. I'm going to skip that one. That's basically about the idea of distributed wind shock. So how do you put together a line profile? Well, basically, the underlying idea is that they're optically thin. This is a mixed blessing. You don't get depth information from optically thin. So when you have the photoabsorption, you also add some depth information as well, because the photoabsorption is itself energy dependent. But basically, you have a kind of emissivity here. You have a velocity spread, and you integrate over the volume. All right, and then you have different lines with different responses for that emissivity. So I'm really talking about cooling by emission lines. And then what this picture is illustrating over here is with the observer to the right, those two cones are back front symmetric when you have an expanding wind. And so you just have more optical depth, more column depth to the far side of the wind on your left than to the near side of the wind, which is on your right. And so you get, you break symmetry in the emission line profile shape, which would normally be right-left symmetric in this picture. And in particular, when you have a thin, optically thin line, and you had spherical expansion, a spherical shell, it's one of those bedtime stories we tell ourselves, stars are spherical. But if you had it, okay, see how far we can get with that, you would end up with a flat top emission profile. And when you have a whole sequence of nested shells of different expansion speeds, like you have a velocity law, then you would have a superposition of these flat tops. They have different widths according to the shell that's producing them. They have different heights according to the process by which you're making those photons, but you basically have a superposition. That's a problem, because if the velocity law is non-monotonic, you still got the superposition. You still have, there's a uniqueness problem in going from the observed line profile back to the distribution. And that's where this photoabsorption could be helpful. But nonetheless, the name of the game here is what causes deviations from flat top. That's it. That's pretty much the game I play. So I'm going to talk about that a little bit. Speaking to the photoabsorption, over on the left, the dark curve is basically a kind of a standard ISM photoabsorption cross-section. And then when you have hot stars, you can have hydrogen is almost always ionized. Helium may be somewhat ionized. So there's some O-star, Wolf-Rayet star cases, nitrogen and carbon rich, and it just shows you how it alters the transparency of the wind. Over on the right, nice image from this paper showing the locus of points where tau equals some number like 1, 3, or whatever for an observer off to the left, your left, in the red. And so that kind of shows you where photons are escaping from. And of course, that's energy dependent. So you have different degrees of transparency depending on what energy you happen to be working at. So here are my flat top profiles. They don't look flat top right now, but over here is flat top. This is the blue shifts in this normalized coordinate. Over on the right, it's not flat top because I have stellar occultation. And then as I increase wind density and start to have some photoabsorption, I make the line weaker, and I also get a deviation from flat top even on the blue side. But this is flat tops are very nice for just illustrating basic ideas. Real world doesn't work out quite that way normally, although novae can sometimes show flat top profiles and stuff. But anyway, you're expecting things like suppressed emission on the red side, peak blue shift in emission, maybe a centroid shift, that sort of thing. I've heard some at different times about resonance scattering. This is resonance scattering inside a line. That changes the direction of escape. So you can also get a deviation from flat top if your line is thick. And then here's much more realistic set of wind velocity laws. Instead of constant expansion, you ramp up from a slow speed at the wind base down near the star to some terminal wind speed, like 2,000 kilometers a second. And they're playing some games with parameters. Now I'm just like breezing through this because I'm not fitting any data. And I'm not trying to demonstrate anything. What I'm really trying to do is just like share the range of possibilities and how to put these pieces together. In particular, expansion versus things like rotation and stuff. So some of these parameters are the nature of the velocity law. Beta is a knob for that, whether I rapidly increase the terminal speed or more sluggishly do so. You can see that you never quite get a flat top. These are kind of like far out in the wind, but you still have some photo absorption kind of effects. And then there's also an idea of volume filling factor. How's this stuff distributed? So there's a whole bunch of different possibilities there. So those, you got to play those games in the idealized space before you start tackling data and try to interpret things. Here's a couple like theorist kind of plots. This is an optical depth down here, and maybe I'm just asking the question, how do I get some moments? That's a common thing for an observer to do. I mean, if you have an emission line, you kind of like, where's the centroid at line center? No, red shift, blue shift. We just heard something about shifts a moment ago. And also the line width, you know, if you're fitting the Gaussian or something, is it broad or is it whatever? And so here are some predictions from those kinds of line profiles with photo absorption. But in the observer space, you might want the thing on the right, maybe. You want to just deal only with the observables. You just want full width, half max, and where's the location of the peak. And you're going to have to remind me of my time as I go along. So, and then this one, I just indicated this is where the half max points are on the red and blue side, and just showing how the whole line appears to shift to red shifts. I'm often doing things in these normalized velocity shifts. That's normalized terminal speed. So these are broad lines, and the shifts can be significant sometimes. All right, so let's bounce through some cases. Here's one I like that actually does have application. This is one of these flat top profiles with some knobs for the filling factor, but it's constant expansion in the photo absorption. And this is actually real data, Wolf-Rayet star, WR6, EZ-CMA. And this shape, which I think Dave likes to call a fin shape profile, actually kind of fits the data, the line profile, the stronger lines, fits it pretty well. And so there you're actually playing the games in the idealized space, finding an application. And what it's suggesting is that since the wind doesn't come off the star at terminal speed, this line probably forms far away, okay? So you're not seeing deep into the wind. There are porosity effects. We know that winds are not smooth, but can become clumpy. There's all kinds of evidence for that. What clumpy does is allow you to have more avenues of escape, geometrically speaking, for the X-ray photons. In other words, you can waste optical depth by concentrating it spatially. Here I'm using a kind of funny velocity law. I'm using like a supernova velocity law, nova one, V goes like R, linear expansion. And just looking at playing some games that you would like to constrain, such as how does the opacity vary with distance in the wind? I'm using U as an inverse distance here, but maybe X-rays are not formed close to the star, but form far out. Maybe they go all the way down, different kinds of things. So you tell me where the X-rays are at, and I can play a whole bunch of games and get different effects. So often you need other constraints. You need other information besides just the line profiles themselves. Maybe you need something from the UV or the visible or polarization or something. What about rotation? I decided to play with rotation a little bit. Turns out several of the massive stars that have the best data sets are actually kind of rapidly rotating. And so I took a model with a rotationally distorted wind and thought about my flat tops and decided what would happen. So this is an expanding wind, but it's rotationally distorted. So it's kind of bipolar, basically. These are a set of pull-on winds. These are equator-on winds. And then the rotations go from 0 to breakup, critical breakup, right? In omega squared. This one's interesting because it goes to 0 at line center. What's going on there? Well, as a pull-on view of a bipolar flow, in this model, which is peer review literature, okay, but it's just a model, somebody's model, push it to its limits. The equator is a place where at critical breakup, you have no wind, but that corresponds to the plane of the sky. And in spherical expansion, that corresponds to line center. If you use a more realistic velocity law, once again, low rotation, high rotation, different viewing inclinations here. What I kind of discovered from that particular wind model for rotational distortion, it doesn't look obviously like it's not a spherical wind and outflow, but the rotational distortion allows for greater transparency overall. The lines are basically larger, stronger, sorry. Took a magnetosphere. Oh, there we go. I may have messed something up. I took a magnetosphere, which is in the upper right, and that's all hot gas in the red and yellow, and you get kind of double horn profiles. Turns out when you have solid body rotation, this magnetosphere is so strong, it's just everything's co-rotating. When you have spherical expansion, you have back front symmetry in your isovelocity zones. What are the surfaces that produce emission at a given observed velocity shift or energy in your line? When you have solid body, you're left-right symmetric, and you also get a flat top, as it turns out. And so what happens here, and I kind of lost my screen somehow. So what happens here is when you have this kind of thing, it's like a torus, right? What are you throwing away? The stuff that's top and bottom, which means you're throwing away emission at line center. And that's why you end up with the double horns. I'm about out of time. Clump bow shocks also give you double horns. Why? Because a bow shock is a little bit like a one-sided bipolar flow. So this is a clumpy wind where I have maybe a slow clump and a fast wind, and it overtakes it. So it's an attempt to try to get a little bit of 3D granularity of what the wind distribution might be like, because we know they are clumpy. And I got a couple minutes, right? Let me do this one. What I did was I took the wind bow shocks and I did a distribution. I basically placed them randomly and then thought about co-adding them. And when you convolve them with a realistic kind of response, sort of like Chandra, you get things that look a little bit like a mishmash for these are small numbers of clumps and large numbers of clumps. So you get something that looks like the other old wind profiles, but got a little bit more going on in structure. So I think what I'm going to do is jump forward. I'm going to say something about FIR lines. My time is up pretty much. There is a way for the next generation of telescopes. My examples may not be the best. They were a bit quick and dirty, but in UV bright stars, F to I ratios are used to figure out like how close the X-rays are formed, because you can do pumping of that F line. And so there is a way to do line profiles for F, I, and R separately. And I just have some illustrations here for a grid of models where blue, black, and red are the different components, and you might be able to see some distinctions. I think my V goes like R is not the best case to show. So anyway, if you're interested in line profile modeling, come find me and talk to me about it. I'd love to see what kind of data you're wrestling with and see if there's some possibilities here. Thank you.
Thank you. I've pushed you enough that we have time for a question or two.
I just want to say that about a month ago, there was a publication by Munoz Darias and collaborators, I think, about machine learning definition of categories of line profiles in optical spectra of low mass X-ray binary black holes. And so they've done a good separation of what they have in terms of observation, but they pretty much have no idea what they have physically speaking for the interpretation of the line profiles. And these look very much like what you've shown us. So you should definitely, I should get you in touch with them, because it's going to be very interesting, because they've been trying to find people that can tell them what the hell they're looking at. And you seem perfect for that.
Thank you.
So thanks for doing this work.
Maybe I could talk to you later.
Is there one more quick question?
In that case, I'll just say that I am also involved with something called the Polestar UV spectropolarimetry mission concept. So if anybody has an interest in that, feel free to come find me and ask some questions.
Thank you. Our next talk is remote by Dave Principe on the top over there. It's a 3-minute talk. If there are any questions, because it's a 3-minute lightning talk, please put them on Slack, and I'm sure Dave will be happy to answer them later. Dave, go ahead.
Thanks, Moritz. So hi, everyone. My name is Dave Principe, and I'm a research scientist at MIT in the Chandra HETG group. I'm here to advertise for an HETG legacy project several of us are working on, which utilizes 70 epochs of HETG observations of the ONC and the Orion Nebula Cloud star-forming region, taken over about 2 decades. And if you do have any questions at the end, several of these members on the team are in the room, so please feel free to go find them or ask me on Slack. So at about 400 parsecs away, the Orion Nebula cluster is the nearest massive star-forming region. This cluster contains several thousand low and intermediate mass stars, as well as a few massive stars. Young stars are really important to study because the first 10 million years of formation are characterized by dynamic astrophysical processes. These help set the conditions that strongly influence the star and any orbiting planets for the remainder of its long life. Here, I'm showing an infrared and X-ray image of the ONC, where the X-ray image comes from a previous 800 kilosecond ACES imaging campaign of this star-forming region. In Getman et al. 2005, this group characterized the global X-ray properties of over 1,600 young stars using ACES imaging spectroscopy. The Orion HETG Legacy Project is a collection of observations using GTO and GEO observations to once again view the ONC, except this time with the HETG instrument. Shown to the right is the full 70 epochs of ACES data merged together, highlighting the complexity of this field. The beautiful spectrum you see in the outer portion of the image is from the massive star Theta 1 Ori C at the center of the field of view, the brightest source by far in the field, and taken at different roll angles. Every X-ray source in the field of view disperses its own characteristic X-shaped spectra onto the ACES CCD, although only those with sufficient counts can be extracted for use with high-resolution X-ray spectra. HETG observations of crowded regions like the ONC are complicated to reduce because the dispersed light from one star might overlap with a point source or dispersed light from another star. These issues can be mitigated because Chandra's excellent on-axis PSF is able to discern between the cluster members, which are often located within 5 to 10 arcseconds of each other. This issue makes studying stellar clusters further than about 400 parsecs where the ONC is, with high-resolution spectroscopy, pretty difficult. So to give you an idea of that, here I show you just one 50 kilosecond epoch from these observations. And I want to focus on the intermediate mass star TU Ori, where the extracted spectral region is shown here in teal. Here, in this particular case, we need to deal with confusion from the dispersed spectrum of COOP 394 up here. This guy's going to disperse its arms over here, and it intersects with the spectrum of TU Ori. And in another way, these 2 point sources, the 0th order non-dispersed spectrum of COOP 1462 and 1424, these also land on the spectral arm of TU Ori. So these sort of have to be considered when you're doing spectral extraction and fitting. And so we wrote a Python routine to identify the locations where all these things occur for every single source we're interested in extracting, and identifying where these things can be confused so we can account for them in spectral fitting. So we've produced a set of clean spectra for spectral modeling that will be released to the public. Well, I don't expect anyone to digest this large, small fountain table of model parameters fit in a 3-minute talk. I did just want to emphasize we have a high quality set of about 40 spectra from different sources in the ONC. These include massive stars whose X-rays show signatures of shocked stellar winds, and intermediate and low mass stars over here, whose coronal X-ray emission provides insight into coronal abundances for stars that form from the same molecular cloud material. Moreover, several of the sources in our field of view were identified to have flared, and many more studies within our group are underway, investigating the role X-rays play in radiating circumstellar disks and identifying accretion in young near and low mass stars in this particular field of view. Thank you.
Next, we're going to hear about CH Cyg. You can either put that around your neck with a magnet on the back, or tape it on. That would be fine. I'll give you a 3-minute one.
Okay.
It's not letting us see the cursor for some reason.
Okay.
Otherwise, it should be good.
Okay. Thank you. I'm Jesús A. I work at UNAM in Mexico, in Morelia, and I will tell you about the crazy ideas that we've been having to explain the X-ray emission from symbiotic stars, particularly from CH Cyg. Just let me start by saying that I'm not supposed to be in this session because it's a binary system, so just bear with me. A symbiotic star is anything, a compact object that is accreting material from red giant stars. So this means that it could be composed, this compact object might be a white dwarf, a neutron star, or a black hole. But here, I will just refer to as symbiotic stars of those that have white dwarfs. And of course, I don't need to convince you that these are important because if they are accreting material, they can be progenitors of type 1a supernovae, and they have cosmological consequences. So what is the origin of the X-rays in symbiotic stars? This is a very nice review from Mukai in 2017. So if you want more details that I cannot give you today, just go and read it, because I am not an expert in this. So there's 3 or 4 types. So there's the extreme sources, which are produced by nucleon burning at the surface of the white dwarf. And that's why I draw it purple here. They might be produced by shocks, winds, interactive with the companion. These are defined as beta or gamma type sources. And finally, those that have that are highly absorbed and they have hard X-ray emission. And sometimes they could be a combination of the several other ones that I just said. So these are called beta or delta types. So there are not many symbiotic stars that are resolved. This is actually one of the few cases, or the only case, that's the extreme, very nice case. This is our query. The optical is what you see in red and green, and then in blue, this is the X-ray on the left, the X-ray emission detected by Chandra, which is mostly the jet, the precessing jet, interacted with the circumstellar material. And then recently with XMM-Newton, we detected this extended emission that is filling up this bowl-shaped cavities. What we think is happening is that the jet is just blowing up cavities larger with this hot gas produced by the jet. So again, there are not many spatially resolved symbiotic stars, but we, of course, only have spectra. And in particular, I want to mention this CH Cyg, the one that I want to talk today. This is a comparison between these symbiotic stars with 3 different Safer-2 galaxies. So this is a very old paper from 2006, where these people suggested that the physics might be the same, reflection, accretion, the same happening in AGNs, it should be happening in symbiotic stars. I won't go into the details. There's a lot of X-ray observations and papers studying CH Cyg. It has been observed by Exosat, Rosat, ASCA, Chandra, Susaku, XMM. This is a list of papers. But of course, because this is a high resolution meeting, this is what we did. So we took the available high resolution spectra of CH Cyg. On the top, you can see the XMM-Newton data and the Chandra to Meg and HEC instruments. So mostly XMM detects the softer region of the spectrum, and the Chandra detects the higher energy line. So we have some triplets and a lot of emission lines. So because of this, we were able to model the spectra and to obtain for the first time the actual abundances of the X-ray emitting gas. And this is just on the lower panel. This is just a comparison of the optical spectra, which is mainly tracing the gas from the red giant companion, and then the abundances predicted by modeling the RGS data. And of course, this is the temperature predictions. This is unconstrained, of course. And these two are soft components with relatively low extinction or column density. We can also use the triplets to estimate temperatures. So the multi-temperature components, we detect the helium-like triplet, the neon 6, oxygen 7, magnesium 11, and silicon 13. Of course, we can use the fluxes of the different lines, and then we can predict or estimate what are the temperatures of this multi-temperature plasma. These two are mostly the same, and this is also, these are they don't have errors because in this case, the intercombination lines, they're very marginally detected. Of course, we also, and this is not the first time that has been done. So people have been, Mukai in 2007 predicted that the iron lines are varying depending on the epoch of the observations. And we also see the same trend. The important thing here is that the fluorescent line, which is the 6.4 kilo electron line, is fluctuating in flux compared to the other ionized lines. So that means that somehow what is producing this fluorescence is the material, the disk, or whatever, the wind of the companion is changing and is giving us different column densities. So one way what we wanted to do is how can we characterize this circumstellar material that is producing the variation on the fluorescent line. So let me just go into what we usually do is that we just go and fit models with different components and try to have a statistically accepted model with something reduced chi-square about 1. So here I'm showing you that the model, this is the same data, and then with different models. The only difference is this intermediate line here, which is here is a third component unconstrained, and then some reflection model from XSpec. So this only shows that we need something to model the intermediate range between 2 and 4 kilo electron volt. And then whatever we put there, it works. But we need a physically driven model. Okay, so and the other thing that I personally don't like is that we sometimes just add a Gaussian to fit some line. And this is something that I don't like. Well, I want to repeat that I don't work in this field normally, but this is something that I couldn't grasp. So this is just adding a Gaussian is not, strictly speaking, not a physical process. So what we did is we used the AG because, as I said, some people have suggested that symbiotic stars look alike AGNs. So we went and took some of the tools that AGN people use. So we used the radiative transfer simulations from Reflex. So what this code does, you have a source and some medium, then you transfer the X-ray photons, and then you have some synthetic emission. So we use the total X-ray luminosity that we obtain by modeling this. And then we can try to run a large number of models to try to parameterize extinction, the thickness of this disk, radius, and different other parameters. So what we actually found is that we were able to produce a better, in my opinion, model. So we do need two soft X-ray components, the 0.18 kilo electron volt, 0.7, and then the heavily extinguished, which is yellow. I think it's not the best color choose. And then we don't need to add artificially this Gaussian line because the reflection naturally produces the 6.4 electron volt, and then it also has some contribution to the soft X-ray band, or down to 0.3 kilo electron volts. This is just a zoom for the 3 lines, so you can see that the reflection and the heavily extinguished component, material around the disks, they produce naturally the 3 emission lines. So one is due to reflection, and the other 2 is because there's high temperature plasma there. And I think I went too fast. And so what I want to say is here that this was the first time that abundances were accurately measured for symbiotic star in X-rays. There is currently no other source that we can do this because this is one of the brightest. So in order to perform such complex modeling, we need better X-ray spectra for these sources. So hopefully the new missions will help us with this. And we think there might be a way to come up with a unified scenario for the X-ray emission from symbiotic stars. This might be a crazy idea. And that's all I wanted to tell you. Thank you.
Yeah, I just want to say you have 4 more minutes to talk from now on.
Damn. That means more questions.
So I thought you will be able to estimate the mass of the white dwarf. That's I think will be nice goal.
Yes,
from temperature distribution, right?
Some people have done it. Other X-ray studies of this source have done it. That's why I didn't want to go into that.
But you know, you have physical models, so
Yeah.
called, right? Supposedly you could do a better job.
Yeah, of course. This was just a toy model to demonstrate that a reflection component, it's better than just adding more and more components.
Have you considered other spectral models, for instance, partial covering fractions or, I don't know, optical, thermal with optical thickness?
We haven't. So this is an ionized disk. And of course, we haven't tried other like morphologies like I don't know, opening angle disk, or this is just one model that fit. And we are proposing that this is more similar to AGNs. This is the idea we're proposing right now. The next step is to start like exploring different other parameters. For example, there are a couple of other symbiotic stars that actually in time, multi-epoch observations show that the soft X-ray emission goes up and the harder goes down. So these are all other phenomena that we still have to come up with to explain in order to come up with a unified model for this.
I work on cataclysmic variables, so I was wondering, it's related to that question in the chat. Has this been tried, this reflection model, for other CVs, just not symbiotic stars, or is there something in the winds and the red giants that makes this more suitable?
Novae are main sequence stars, right?
Right.
So I guess the extinction is less, given because these red supergiants have like lower temperature, higher mass loss rate. So I don't know how exactly it will be, but the thing is that the only thing you need is that the creation of an accretion disk, and that's what's causing the reflection.
Right.
Mm-hmm.
Yeah, I see my name there in the chat. You want to comment? There's actually not a relation. I also thought, but you know, what I study is actually nova explosions, where the nova ejecta collide with the stellar wind of the companion symbiotic. So stay tuned for Thursday morning. But I had a question because you finished your talk with that you need better data. But my impression is like the second point, for example, the 2 to 4, there's mission that you have already detected with the present instruments that where you need modeling. So it's not quite clear to me what you mean, what the future instrumentations can add.
In particular, I'm referring this area, the spectral area, because it's.
But you already have the data.
Some of them just have a few points. Yes, for some sources, we don't have a large number of because of the 300 symbiotic stars, we only detect 60 in X-rays, and only about 12 are beta delta type like this one, and only about 3 or 4 have very good quality in order to do this. So if we want to go and propose a unified scenario, we need more sources than those.
So more sensitivity.
Yes.
Okay.
Thank you. Hi, Jesus. This is a minor thing in slide 11. You said that the reflected model produces the 3 lines, but no, it wasn't this one, the one with the, yes, this one. But I don't see the 6.4 line reproduced by the reflection here. The reflection is the
orange.
Oh, it's the orange. I thought it was the other one. And then one more comment. What do you do with the X-ray power law that is normally present in AGN? In this analogy, have you thought about it? Or
so in like input. So what we just did the same thing. We just defined that the X-ray luminosity is a power law with a gamma of 2. This is what we said.
There's 2 comments or questions from the remote people. One is are nova with red giants and AGB companions, which I think somebody already said. And Sean Gunderson asked, have you considered variable symbiotic stars like AG-DRA?
We are currently exploiting the archive. I have no idea what's the quality of the AG-Draconis spectra.
Thank you. We had a lot of questions. If there's any more discussion, there will be a coffee break later and you can put them on Slack. We'll move on to the next speaker, Vinay, who is going to. You're too fast. I was going to say, let's thank the next speaker while we switch over, and we didn't get that far yet. So our next speaker is Vinay, who's going to talk about some interesting problems with analyzing deep X-ray sources.
I know that it's not sticking. Oh, okay, it's stuck. Yes. Thank you. Good afternoon, everyone. So can I turn off this thing at the? Actually, I don't know how to do it. That's okay. Yeah, I'll probably look here. I'm going to be telling you actually more about symbiotic stars and binary stars. So maybe I don't belong in this session either. So the goal here is basically to sort of tell you about the kind of stuff that our astrostatistics group has been doing. The people, these are statisticians and the students. Margarita, many of you know, is an astronomer at the CFA. So the things that I'll be talking about are going to be about RT crew, which is a symbiotic, and UV set, which is a M-dwarf binary. And the particular issues that I want to highlight is that, high resolution spectra, there is this sort of idea that everything becomes easier, but it's not, it's like, especially when you push it far enough, you have to deal with sparsity, you have to deal with detectability, and then there's always background. So the RT crew bit is about weak lines in high background, and the UV set is going to be about untangling overlapping lines from companions. So first of all, RT crew, it's a symbiotic system at 2.5 kiloparsecs. I don't have to tell you what symbiotics are anymore. And it's a high mass white dwarf accreting from an M5 giant. And it shows flickering with soft flares. So what you're seeing here at the bottom is a time series with the HRC, LETG, and the HETG. And this is, the total counts, and the colors represent effectively hardness. So when it goes up, it becomes softer. Red means soft, blue is hard, and the same thing seems to happen with the aces. And of course, I mean, you see up there on the top the triplet, the ion triplet, the ion K alpha and the ion 25, 26 lines. And there is presumably also a highly absorbed soft component that we try to model in Danekar et al. And what you see over there is the fit, the best fit plotted over the HRC LETG. We actually asked for this observation just to see what the soft X-ray, the lines were in this observation, I mean, in the source. And we couldn't see any because the background was still high at that time. The sun was going down into minimum, background went up, and anyway, you couldn't see anything. And so the goal here was to figure out where exactly all these soft thermal lines, can we even find them? Can we say anything at all about them? So the technique that we decided to adopt here is something called SQG density modeling. The way it works is that suppose you have a model for the background, we'll call it, So let's say the true model is called G, and what you actually, sorry, what you think the background is G, but what you actually observe is F. And what you want to do is take this thing and adapt it to do the analysis. So what you do is you can convert this G and F into cumulative distributions, cumulative densities, and take the ratio that way. I mean, taking the ratio is quite trivial. The tricky part comes in treating this as a distribution, and effectively turning it sideways so that you model it as a function of the quantiles, the U or the quantiles there. And then what you see is that you have a shape that can be modeled with smooth functions, something like a shifted Legendre polynomials. You could even use Fourier transform if you wish, but of course, you have to use lots of components. And then you decide how many terms to use via a model comparison statistic like BIC. Now, the question, of course, why do you want to do all this? Why can't you just do everything the way we've always been doing, which is take the background, scale it, and model it or fit it or whatever. So there are several reasons. One is that this lets you define a data-driven measure of complexity in the background. So even if you don't have a good handle on the background, you can still deal with it as part of your analysis. And then, I mean, you remember how we all used to do source detection, right? We used, well, some of you are too young. We used to calculate signal to noise and measure the flux and see if it was greater than 3 sigma away from 0. And then we went off to doing something better, which was to look at how far away it was compared to background fluctuations. And therefore, we lost the information about the flux, but gained power in the detectability of the sources. We're doing something similar here because we are converting these into distributions. We're losing the normalization, the actual level of the background, but we're only looking at considering the shapes. And this is easily transferable from background to source. It doesn't have to be, the G doesn't have to be a background. And effectively, what this means is a general detection method for arbitrary features of any shape. So this is an example, for RT crew. So we try to find, look for lines in several of the usual locations. Top left is the ion complex up there. And then, there's the ion 17 lines here. Oxygen 8, and then the 3 oxygen 7 lines, and then up top is neon 10. The locations are marked with the vertical blue line, and the size of the line spread function is indicated by yellow, by the yellow shading. So we could find the ion lines, we could detect them. And rather serendipitously, we also managed to find the iridium M edge, because our model does not include any of the, does not include an effective area. It's just the background as it is and converted. And you can see that, it's easily picked up. And there was a line at 16.93 that we also found serendipitously, and it turns out to be detectable, which I want to talk to Chintan and various reflection component people to see if there is anything that could be that there's any physics in there. But we couldn't find detect any of them, and we had to place upper limits on them. So what are these upper limits? So first of all, you don't have to look at all of these numbers. For W1 is that one. And what those numbers are showing in the red box are showing, or how well the background itself is determinable. So in the top, the first one, the background is not well determined to be a flat one. We started off with assuming it's flat, and that's because there is a continuum component under it, which is messing things up. The iridium edge is very strongly, highly significantly detected. None of the others are different from a flat background. This is, and the second set of columns, numbers is trying to test for whether the lines exist in any of these locations, and none of them do. The closest one that we get to is maybe number 6, which is oxygen 8, which is at 24% significance, not very high. And eventually, so then we go on to get actually set the upper limits at the number of counts, and it so happens that these are so much higher than the predicted line locations that we can't rule out, say anything about the actual model that was used. It was extrapolated from higher energies. So the next thing that I want to talk about is UV set. It's a flaring active M-class binary. It's around 2.7 parsecs away, 1,000 times closer than the RT crew. It was observed with HRXS LETG, and there was a massive 100x flare on UV set B on this one. So this is the 0th order image. What we can see is this is what the light curve looks like, and you can we modeled it using something called EBAS, where you take each photon and assign probabilistic measures as to see which source it can belong to. So, and what that does is that it lets you figure out, make corrections for whenever, for instance, when there's a huge flare, it takes that information into account, and you can make corrections to which photon belongs to which source. So the green thing over there was originally wrongly assigned to A, but now was moved to B, and so on. We got greedy, and then we decided, well, how about we look at the oxygen 7 R, I, and F lines that are dispersed in this thing, and can we actually use EBAS to do this? And we said, okay, let's try. And this is what we got. So we, for instance, so we looked at the I to F ratio, the oxygen density sensitive oxygen 7 ratio during the flare and outside the flare. And during the flare, it turns out that there's a 5 times increase in this ratio, which corresponds to about a 10 times increase in the luminosity, and 100 times increase in the 10 times increase in the density, and 100 times increase in the luminosity, and it's almost entirely attributable to density increase. So this is a density flare, not not so much a temperature flare. So in summary, I just want to point out that we did 2 things. One was try to develop a new method to discern deviations in the background model to detect weak lines in high background. Couldn't find any, couldn't detect any, so I had to place upper limits. But there is a strange line at 16.93 angstroms. That's 0.732 keV. So, and then trying to disentangle overlapping lines from contaminating companions, and applied it to UV setting. Thank you.
Thank you very much. Any questions from the in-person audience?
So RT crew didn't work out, but did you try anything else with stronger lines and then just keep subsampling it to weaker and weaker and weaker to put limits on the method?
That's in the plans. But I wouldn't really say that didn't work out. I mean, the goal initially was to falsify the model that we had, and we couldn't. So, we can't rule out the thermal spectrum at soft energies.
Any other questions? And I'll ask on, for your finding things in backgrounds, what do you need for that to work?
At this point, it needs high background and event lists. It works on unresolved, unbinned events. I forgot to mention that, yes.
Any other questions?
And just to follow, the goal is that, in principle, when you have something like Chrism or Athena or one of those things, you could be looking at a weak source sitting in extended emission, and you would be able to pick out and model just that by taking out the underlying background. I mean, the background doesn't have to be particle or diffuse astrophysical background. It could be whatever is sitting next to it and contaminating.
So would it work if you had a point source in the galactic center?
Yeah, that's
with
the
the
idea.
HETG on top of a really strong.
That's an excellent thing. I hadn't thought of it, but yes.
Yeah, on the first point, just to understand, is your method a more robust way to determine what is the level of intensity of a fluctuation in the spectrum, which is actually simply most likely due to a fluctuation and not very aligned? So can we use it for the Capella spectrum, for instance, which has in principle 10,000 of fluctuations, to tell below certain level, this is not aligned?
We might be able to, yes. One point though, it's not the level of the background or the continuum that this is sensitive to. In fact, we lose all information about where the background is relative to the source continuum. It's only the shape differences that pick up. So, for instance, if the background is flat and the source is dropping with the Bremsstrahlung thermal, then we can pick up all those things, and even the weak, maybe the ion lines, that's way below for stars, that sort of thing. So I hadn't considered Capella as a target for this analysis, but that's a good idea. Think about it.
I'll ask the next speaker to come up while we can thank Vinay again. You can flip it on or put it around your neck, whatever you prefer. And then we're going to hear some more about advanced background modeling, presumably things with high backgrounds.
Thank you everyone for coming. So I will also speak about Rebecca for this talk, just like I planned. So basically the goal of the talk is to explain to you what have we been doing with the backgrounds and what we are trying to do next with the background. Okay, I'm a postdoc right now at Stanford. Okay, so I guess we already know what we all know because we hear. So why do we care about the background? I'll talk about the background component. What have been done so far? What are we doing right now? What are the benefit of the new method? And what lesson have we learned from this? Okay, why do we care about the background? It is especially important for us because I study galaxy cluster that which is both extended sources and also faint sources, that the X-ray background sometimes is actually comparable to the science signal. So that means we have to be really careful of studying the background in the case of this object. As most of people already know probably, so the X-ray background composed of three main components. So there will be two components come from the sky and one component come from the particle induced from the detector. So the background component from the sky is come from first the foreground, which is basically a hot gas emission from our own Milky Way halo, unresolved point sources, so like the undetected point sources that are like so it looks like a background, and then the cosmic ray particle induced background that mostly coming from the actual detector, so most people call it strobe background. And then in the case of Chandra, particle background is the most important part, way more important than the other two components. But we actually need all three to actually get a proper understanding of the background itself. Okay, so everybody already know how to do this, but I'm just gonna go through it really quickly. So what do you do with if you wanna actually get some better understanding of the data, just try by understanding the background. So if you have an empty region that is without any source emission, we use the on-chip region as a background for subtraction. The issue of that is because some object is really extended, like the ICM for the galaxy cluster. That means there will be no empty region on the on-chip region for us to use as a background. So then what do you do in the case of there is no region with solid emission? We basically use blank sky background or the SOR background. The blank sky background is basically the combine of all sky background with point sources removed to just get some background. And then the SOR background is our focal position of the telescope, just to get the particle induced background. The issue for both of these is that the sky background is averaged in all directions. So the foreground component and the unresolved point source component have already been averaged out. So we don't really get some information of those, and we have to model that separately anyway. And then the SOR background is again is only including the particle induced event. So what are the challenges from the previous method that I've been talking about so far? So there is a limited statistic because, like, even though on the on-chip data, sometimes we have a really short exposure time. That means our background will also be really low in also short exposure. And then because of sometimes we also have a use really small region on the sky. That means blank sky result can also cause in a really small statistic. And then inaccurate component, it just means that we have a difficulty to actually correctly identify all the components, including the soft foreground and undetected agent population. And then the last thing is a little bit technical. So the loss of resolution with background subtraction, we cannot use the normal C-stat. We have to use modified C-stat, which require at least 1 count per bin, that leading to the reduction in the resolution for both spatial and spectral resolution. Okay, so what are we doing? Instead of trying to get the data, we basically have to model every single component and put everything together into one background X-ray model. And then the 3 components that I was mentioning earlier is the foreground, the unresolved point sources, and particle induced background. And in the foreground, we basically use the low set sub X-ray background as our foreground component. We use some point source detection criteria for the point source, and then we use the SOR background that the Chandra team already have for us. Okay, so for the foreground, we basically create an annulus allow outside the about half a degree away from the cluster signal, so that we can get some soft component for the foreground so that we can estimate the soft temperature for the foreground component. For unresolved point sources, we basically because as everyone knows, the PSF of the let me point with the arrow here. The PSF of the Chandra is basically the work best in the center on axis angle and getting worse at off axis angle. So then we model basically the off axis angle value and the background density to get the sensitivity of the point sources based on those 2 parameters, and then using the luminosity function of the expected agent population to calculate the brightness involved in the unresolved agent model component. And that will resolve in creating the unresolved agent normalization map, which we can then estimate to be our unresolved point sources component. The last thing is the particle induced background or the SOR background. So we basically use a model that have been developed using the SOR background from Chandra, making available by this paper, Suzuki 2021. We have to do some modification and changes so that it can work with for our specific case. But then yeah, the code should be public for this part of the project. So here is what the SOR background look like, and the black line here is basically the model. And then that basically just get all the information about the SOR background in the model form. Okay, so now that we get everything in order, now we try to basically combine all 3 components and try to understand whether the background model will actually work for all the cases. The first thing that we try to do, we call it off cluster region. It's basically a region of the CCD that have no cluster signal, or just a background region on the sky. Okay, so here is okay. I'm showing it as this region here because that's what I first start testing. And here, let me show you the top plot first. So these three color is three different components that I was talking about earlier. So the cyan one here is a particle-induced blackout, is the one that's the most important one. And then there's some soft focal and unresolved agent. You can see that even though the soft focal component is less important, it actually getting pretty important at the soft energy. And so, but then you can see that all three of the model combine into the total blackout, and then that's getting pretty good as you can see on the residue. Let me say that these two components, we don't actually fit anything. We just get it from the model, from the low set, and from the calculation that we predicted. And then we basically just put everything on the plot without any fitting of anything. Okay. And then we can also do the same thing with the surface brightness profile. So the orange point here is the data, or basically how bright is the object is from the center to all the way to the outskirts. And usually what people do is they will subtract the blackout and get all the signal all the way down. But now, since we're not doing any more X-ray subtraction, you can see that the data actually getting flat into a constant at really large radii. And then you can see that each one of these components is a blackout component. And as I mentioned earlier, the first, the purple point dashed line here is the particle-induced blackout, and that's the most important one compared to the soft focal and also the unresolved agent. And these two are the beta component for the galaxy cluster. And then because different chips also have different level of particle blackout, so we have to model different chips separately. And then this also work in all the other cases that we have tried so far. So we think it's getting into a good shape for us right now. Okay, so what did we learn so far? So this method actually have been proven to be surprisingly effective in studying extended objects at large radii of faint objects. So we are hoping that we might be able to study with the same data, we can actually extend it further to even larger radii. And then the backup model is very important to also the future X-ray mission, because we will get a more reliable result. And then even though I only talk about the Chandra in this talk, this approach is also not limited to Chandra. And then other missions like Principe, which have even smaller field of view, will require some of this technique to actually use it to get a better result for the analysis in the future. And that's it for the talk.
Thank you. Are there any questions around here?
So I think it's nice work on especially on the AGN contribution, which detection depends on the off-axis angle, right? So but assume you have to kind of use certain luminosity function to predict the amount of AGN contribution, which is not removed above certain threshold, which is off-axis dependent.
Yes.
Right. So is the cosmic variance issue from region to region? I mean,
it could be an issue, but we don't think it's for us right now. It's not the most important backup component. So right now we don't see any issue so far, because it's basically the least important version. But if we get a better data, it could be an issue in the future, definitely. Thank you.
But not just particle contribution from the store there.
Yeah, that's still.
But that's the traditional people already worked out. So I'm just the most kind of innovative work is to remove the AGN in a unbiased way.
Okay, I see. Thank you. So I think so. What we are doing right now with the luminosity function of the AGN, and then try to get also the estimated of the unresolved point sources. I think it could. I don't think it will be dependent on the cosmic variant too much, but yeah, I'm not sure. We have not tested it, but thank you.
Are there any other questions? Then let's thank the speaker again.
All right.